Good morning. This is our first video in going through Linus Pauling's awesome textbook, General Chemistry. Linus Pauling wrote this text and he published the third and final edition in the 70s. He was probably the best chemist of the 20th century, and he was also a really gifted teacher. And the textbook that he wrote, and he wrote a couple of them, General Chemistry is one, and then he wrote one that deals with quantum chemistry. The textbook is a very advanced text, and it's probably a good idea for any student of general chemistry who really wants to understand the concepts at a good advanced level, or also any student who's majoring in chemistry or physics to study from this text. So it's really well written. He assumes that you're able to follow some difficult trains of thought sometimes. Sometimes when you read something, you might have to think about it before you move on, but it is not beyond comprehension, and it's filled with all kinds of small anecdotes about different discoveries, and some of the story behind some of the names of things. So what we're going to do in these videos is to go through the end of the chapter exercises in this textbook. Now, I'll tell you right now that I have not read this text all the way through, and so I'm going to be doing this as I go. I studied chemistry back in the 90s, and we used a different textbook. So now that I've been teaching general chemistry for about 7 years, I feel like I'm somewhat qualified to lead you through these exercises. Now, I do make mistakes from time to time, as my students will, gladly tell you. But hopefully, if there is a mistake and you see one, then feel free to please point that out in the comments below, and we can talk about it there. So hopefully we'll learn something as we go through these exercises. Before we get started in chapter 1, let's just take a quick look at the text. Here's the back of the textbook right here. If I were you, I would get a copy of this. It's very cheap. Dover puts out some of the best science textbooks out there for really, really cheap. So this is a good one, and there are many other Dover textbooks you should have. If you're studying linear algebra, I would get Shilov's linear algebra. If you're going into I just cannot suggest enough, but there are some really good ones for great prices. Okay, so get a copy. Here are the contents. We're not going to read all through these. I'll just show you. Okay. And 26 chapters, several appendices, almost 100 pages or 80 pages of appendices, so pretty good. Now, the last few chapters actually do not have exercises. I believe the exercises cover up through chapter 23, and after that there's no more. So we'll do our best to make our way through most, if not all of them. All right, without further ado, let's go ahead and check out the exercises for chapter 1. Now, chapter 1 has few enough exercises that we'll do this in one video. So I've written my notes, and the format for these videos will be to what happened? Will be to do handwritten solutions for the most part. So here we go. So you can see here is the answers that I have so far. Now, along with my notes for problem 1, I reference the page number where it discusses this type of stuff. Okay, and again, I'll reiterate that my answers might be a little bit different than what your answers would be. So this is just my take on the problems. And sometimes the answers might not be, fully complete, but I'll do my best. So problem number 1 asks, what is the difference between matter and radiant energy? This is discussed on page 1 of the textbook. And this is a very interesting take. So matter is any kind of mass energy that moves with velocities less than the speed of light, while radiant energy is any kind of mass energy that moves with the velocity of light. So Einstein helped us understand that mass and energy are really the same thing. Okay? So you can convert mass to energy, you can convert energy to mass. Okay, so the difference between matter and radiant energy is that matter is this mass energy that moves with velocities less than the speed of light, while radiant energy is mass energy that moves with the velocities of light. Okay. Number two says, what is the Einstein relation between mass and energy, and indicate the international standard units of the terms in this relation. So number 2, the famous equation is E equals mc squared. This is discussed on page 2. E is the energy in units of joules, m is the mass in units of kilograms, and c is the speed of light in units of meters per second. Speed of light is a constant. In a vacuum, it's equal to 2.9979 times 10 to the 8th meters per second. Number 3. Approximately how much energy in international standard units is needed to raise 1 liter of liquid water from 273.15 degrees Kelvin to 373.15 degrees Kelvin. Okay, see the discussion of the calorie, section 1.3. So if you note right here, in modern chemistry textbooks, we drop the degree symbol, so this was apparently not done back then. And we'll notice things from time to time like this, where our notation might be a little bit different than Pauling's notation, but that's all right. Maybe we ought to change ours to match his, but it's probably a reason it has been changed. Okay, so this is discussed on page 4 of the textbook. In there, it talks about how it takes 4.184 joules to warm up 1 gram of water by 1 degree Celsius. And if you're warming it up from 273.15 Kelvin to 373.15 Kelvin, that's a 100 Kelvin increase. And it's also a 100 Celsius increase, because the size of a Kelvin equals the size of a Celsius. So going up 100 Kelvin is the same as going up 100 Celsius. Okay? And if you're dealing with 1 kilogram of water, that's 1,000 grams. So we have 1,000 grams as a mass. We're increasing by 100 Kelvin, and it takes 4.184 joules per gram per Kelvin to increase the temperature. And so to calculate the energy, it's 4.184 joules per gram per Kelvin times 100 grams times 100 Kelvin. You can see the gram units cancel, the Kelvin units cancel, and you get 418,400 joules. So 418,400 joules. All right. Number 4 asks to verify the following method for converting temperature on the Celsius scale to temperature on the Fahrenheit scale, or the reverse. You add 40, multiply by 9/5, and then you subtract 40. That's to go from Celsius to Fahrenheit. To go from Fahrenheit back to Celsius, you add 40, multiply by 5/9, then subtract 40. So let's verify this by converting two different temperatures from Celsius to Fahrenheit and then back. So how about let's choose the freezing and the boiling temperature for water. So the freezing temperature in Celsius is 0 and the boiling temperature is 100. And in Fahrenheit, it's 32 Fahrenheit and 212 Fahrenheit. So let's see if we can convert those, to the Fahrenheit. All right, using this method. So Celsius is color-coded green, Fahrenheit's color-coded pink. So to go from Celsius to Fahrenheit, 0, we add 40, multiply the result by 9/5, and then we subtract 40, and we do in fact get 32. And to do 100, you add 40, multiply the result by 9/5, and then you subtract 40, and you do get 212. And then you can go back again. Going back, you change the factor to 5/9. So 32 plus 40, you multiply that by 5/9, and then you subtract 40, and that does equal 0. And then 212, you add 40 times 5/9, and you subtract 40, and you do get 100. So it works. Kind of a cool formula to go between Celsius and Fahrenheit. So, got my Hershey coffee cup. By the way, Hershey the cat, I'll show you. There she is. Hey, kitty. She's hanging out on this Sunday afternoon. Here, maybe we'll put her in view. So, what's the next one? The next one is an interesting problem. Number 5. Mercury freezes at -40 Celsius. What is its freezing point on the Fahrenheit scale? Okay, so we just did this. Let's just convert another one. Let's take -40 Celsius. We add 40. Okay. That would be 0. And then we multiply that by 9/5. Still 0. And we subtract 40. And we get -40 again. So it's very interesting that Celsius and Fahrenheit are the same number at -40 degrees. It's the one unique temperature. So I like that problem, and perhaps I'll ask it at some point on a quiz or exam in one of my classes. So number 6. Number 6, let's read through number 6 right here. Okay. For each of the following systems, it wants you to do 4 things. Okay? 1, state how many phases are present in the system. 2, state for each phase whether it's a pure substance or a mixture. 3, give the constituents of the system. And 4, give a set of components for the system. Okay? So the first system is a flask containing saturated aqueous solution of salt and several crystals of salt. Okay, so you have some flask and you have salt water along with some extra salt crystals in there. Well, there are so here are the notes here. This is discussed pages 8 to 10, right? So we're interested in the phases, whether it's a pure substance or a mixture, the constituents, and the components, okay? So for the salt water, there are 2 phases. You have your salt water, your aqueous salt, and then the salt crystal. Okay, for each of these phases, is it pure substance or a mixture? Well, the aqueous salt phase is a mixture. You got salt in the water. But then the salt crystal phase is a pure substance. It's just salt. Now, the constituents, the textbook does state that constituents are identical to phases. So there are 2 phases. That means there are 2 constituents, aqueous salt constituent and the salt crystal constituent. So that's how I interpreted the textbook. Okay. Number 4, the components of the system. There are the components are how many kind of chemicals do you need to regenerate this system? Okay. There are 2 components, water and salt. Okay. So that was for A. for B, we have an evacuated sealed quartz tube of 100 milliliters volume containing 10 grams of pure zinc heated until about 1/2 the zinc is melted. Okay, so you have, imagine some evacuated tube. You have the solid, the liquid zinc right here. And then I imagine there would be a tiny bit of zinc vapor up there. So you got the solid, the liquid, and then the gas up there. So I think there would be 3 phases: the solid zinc, the liquid zinc, and the vapor zinc. Okay, all 3 phases are pure, they're just zinc. Solid, so again, the 3 phases are the 3 constituents. You got the solid zinc, the liquid zinc, and the vapor zinc. So matches in one component. Okay, zinc. You put some zinc inside this tube, you could regenerate all 3 constituents, all 3 phases. So the last one in this problem is basically the same as B, but instead of just zinc, it's 10 grams of a copper gold alloy. Okay, so again, I would think that you would have 3 phases: the solid alloy phase, the liquid alloy phase, and some of it would even be a vapor up there. Okay, so probably look the same. For all 3 of these phases, they're all mixtures. The solid phase contains a mixture of copper and gold. The liquid phase also contains a mixture of copper and gold. And then the vapor phase, I imagine, would have some copper and gold vaporized up there. A tiny, tiny, tiny bit. Okay, now the 3 phases match the 3 constituents. You got the solid alloy, liquid alloy, and the vapor alloy. And I would say 2 components: copper and gold. Okay, those are needed. These 2 components are needed to generate the entire system. All right, so 7 is talked about on problem on pages 11 and 12. What is meant by intrinsic property of a substance are odor, shape, density, color, weight, taste, luster, area, magnetic susceptibility, and heat capacity. Are they intrinsic properties? And then which of these properties can be quantitatively measured? So an intrinsic property of a substance are those that are not affected appreciably by the size of the sample or its state of subdivision. Okay, so how much and also how finely cut up is it? So if the property doesn't matter, doesn't depend on those, then you would say it's intrinsic property. Now odor, I would say odor is probably an intrinsic property. Depending on how, it probably doesn't matter how much of the substance you have, it probably still smells the same. And also, no matter how finely cut up, it probably still smells the same. But I have a little question mark next to this because it would be perhaps more, intense odor. Okay, if you have a mist of lemon juice versus a just a beaker filled with lemon juice. Okay, so the mist would be more intense, but it would smell the same way. It would be the same type of odor. Okay, so I'd probably say it's intrinsic, but if intensity, if odor depends on intensity, more intense odor is different than less intense odor, then I'd probably say no. But okay, the shape definitely depends on how much substance you have. A substance, you cut it in half, it's a different shape. So that is not an intrinsic property. The density is an intrinsic property. Okay, you have a substance that has a certain density. Okay, you cut it in half, it still has the same density. Density is independent of the amount of material you have. Okay, or its state of subdivision. If you cut it up, each one of those tiny little morsels would have the same density as the overall thing. The color, I would say color is not an intrinsic property. That's kind of weird. The textbook actually discusses how for finely divided substances, the color basically uh, fades away. Okay? It fades away. This is discussed on pages 11 and 12. So the color does actually change. Now, I don't know actually if this is related to intensity. So maybe the more finely divided a substance is, the the more intense the color or the less intense color. I can't remember, but it basically fades, whether it's finely divided or not finely divided. And the textbook says it's not an intrinsic property. Okay, but it seems to me like this is kind of related to odor. You know, for the same reason, I might want to say that that's not an intrinsic property because, you know, the odor kind of fades away if it's not finely divided versus if it is. You know, if you have a beaker of lemon juice and you can't really smell it from over here, but if you missed it, you can. Okay, so it's more intense for finely divided. So it seems like the same sort of thing is happening with color. Okay, weight is definitely not an intrinsic property. You cut a substance in half, it weighs half as much, so its weight changes. The taste, I would think that probably is an intrinsic property, but again, the taste can become more intense depending on its state of subdivision. Okay, so I don't like these question marks, but that's my take. All right. Luster, it's sort of like how shiny the material is, right? I would think that's not an intrinsic property because you have a nice smooth piece of metal, okay, and then you know it's very shiny, very lustrous, but then you you basically cut it up, you grate it up, and it would not be lustrous. So I would say that's not an intrinsic property. It depends on the subdivision, right? Area is definitely not an intrinsic property. You have, you know, a substance, you cut it in half, you basically increase its surface area. And if you pulverize it into powder, you would increase its surface area a lot more. Magnetic susceptibility, I would say it is an intrinsic property. You know, if you can, magnetize something, it probably doesn't matter. You know, its ability to be magnetized doesn't matter on how much you're talking about, okay? Or whether it's finely divided. Heat capacity is not an intrinsic property. Now, heat capacity is the amount of energy it takes to warm a system up. Okay, if you cut the system in half, it'll only take you half as much energy to warm it up. So it's not an intrinsic property. Specific heat capacity is. Okay, there is a difference between specific heat capacity and heat capacity, but heat capacity is not intrinsic. It does depend on how much you have. Now, the last part of this problem asks which of these properties can be quantitatively measured. I think if you're creative enough, you could probably quantify all of them. Okay, probably all of them somehow. Odor, even odor, you know, there are chemical receptors inside your nostril which are affected by chemicals, and if you could somehow measure how many of those chemicals are hitting a receptor, you know, per unit time, that would somehow quantify odor. Shape, you know, imagine if you're creative enough, you could quantify all of these. If you're not creative, I would say no, you can't do this one. Shape would be pretty hard. Color you probably could, right? Because that's a wavelength of light, you know, that's a number. Quantifying something means associating a number, right? So, luster, you know, if you're not creative, you probably couldn't do that. Taste, probably couldn't do that one. So the rest of them, I think, you know, even non-creative people could quantify. Density, has a certain number associated. How many grams per milliliter? Color, it has a certain wavelength. Okay. Weight, put it on the scale. Area, you can calculate area, measure the surface area somehow. Magnetic susceptibility, that's a well-defined physics quantity. Heat capacity, that's a well-defined physical quantity to physical property. All right, so there you go. That's what I think of chapter 1 exercises. So until chapter 2, aloha, and I'll see you next time.